Hello and welcome to E233. I'm your instructor, Gregory Myers. In this video, we're going to take another look at our P5 modified, which is an older version of the P5 modified that focuses on our physics demo series. This video assumes a number of things that you've watched the physics demo, have went through some of the structure examples and the fundamentals demo, as well as having completed a version of the P5 that is similar in concept to this P5 modified series. And specifically, it would be helpful if you'd watched the earlier versions of the video focusing on the P5 modified setup and the similarities and differences between the two. This video, we're going to focus solely on our beam calculation and how it differs or what changes need to be made between our P5 and our P5 modified. And to begin with, what we want to do is we want to focus on the structure. You should notice that the structure looks very similar to the arguments that were passed to the function signature in your earlier version of your P5 or the simple supported beam version 4, the unmodified one that had multiple arguments. In this particular example, what we've done is we have simply created a structure that we are calling beam underscore results, and we are using it to wrap around each of the fields that we need to calculate the results for our simply supported beam. So essentially what we have is we have a bunch of parallel arrays that are being wrapped by a structure. In addition, we have some individual values, particularly that for the int n, which simply keeps track of the number of elements in our parallel arrays, and also the L, which is the total length of the beam. Now you'll notice here that I've done something very subtle between the P5 and the P5 modified. Whereas before we would call this value W array and this value A array, as well as the R1 array and the R2 array, I have instead left them as WA, R1, and R2. Now you might think I did this to confuse you. Well, the answer is sort of. Instead, rather than think of it as confusing, I want you to understand that the field names in the structure can actually match variable names outside of the structure. And we'll see how this works. Specifically, in this example, we'll see how we can take the W as the singular value that is being collected from the user and ultimately turn it into an array that appears to have the same name, but is encapsulated inside of our structure. Likewise, we'll do the same thing with our R1 and R2. Now, there really isn't a name conflict with our A. If anything, in the earlier video, when we called it A underscore array, it was just to reinforce a point, help us understand that it wasn't simply a singular value. So let's go ahead and take a look at the function itself and see what changes were needed to be made to make this one work. And you'll see that structurally, it looks very similar to our P5. Or the version 4 of our functions, the unmodified one that accepted multiple arguments. And we have to go through and do each of our validations for our W, our A, R1, and R2 to see if they are in fact valid arrays. Now, this is an unlikely scenario in this particular example. So if you don't understand this, why we're doing this, don't worry about it. You'll see that in the future. It's going to be difficult for us to run into this scenario. It just helps us get into the habit of validating even the arrays themselves. But what we want to focus on is the use of the example with the dash and the greater than sign to prefix each one of our fields. The idea is that all of the same steps that we would have done in the project if we had provided these as separate values can be done as if we have passed a single structure, in this case by address, which allows for us to modify it. We just simply have to prefix the name of the address with this then dash greater than sign to say that we're looking at the value associated with that field. So once again, don't focus too much on this yet. We'll come back to this. As a matter of fact, we'll make some modifications to this. This just sort of gets us started on the thought process. But rather what we want to do is we want to focus on the need to validate our L, our N, for both the minimum value and the maximum value. That point, then, if it fails any of our validation tests, we simply say results are equal to exit failure, and then the calling function can decide what to do from there. Once we have validated each one of our values, then you want to focus on the code that actually calculates the reaction forces for each load at a given point. In other words, for a W at a specific A. And once again, we're going to leverage these parallel arrays, but this time they are going to be the arrays that are encapsulated inside of our example structure. And so if you look back at your P5, essentially this code is identical if you simply remove this portion right here. So basically everything that would otherwise be addressed or accessed individually as individual arrays is now just simply prefixed by the name of the structure, followed by this dash greater than sign to say that we want to reach in and we're wanting to modify the value, in this case, in these parallel arrays for R1 and R2 based on the index inside of our for loop. Assuming that all of our calculations have been successful, we return our results, and then we go back to main. Now we want to take a second to look in main, particularly at our variable declarations, to see what we have had to change. And so you'll notice here right off the bat, I have to create a variable of type beam results. So it's a structure. We're going to call it beam underscore example to sort of keep in line with our earlier videos. And in addition, we also created some additional variables here. So we have our A underscore delta that we used before to calculate essentially the distance between locations that we were applying the load to. We still have a singular W and we have a singular L, as well as the int N that we have now reused multiple times. But we also have singular values for the R1 and R2. Now, this probably sounds a little confusing at this point. How can we have an R1 inside of our structure and an R1 as a standalone variable? Well, the reality of it is that they don't see each other. In other words, you have to look inside the structure to see the field R1 that is associated with the structure. And for that matter, we have only created a single beam results. There could be multiple beam results. In other words, you could do this calculation multiple times for different beams, different loading, and so on. And so each of these variables could then have a field inside of them called R1 or R2. And there would be no conflict because fundamentally they wouldn't see each other. Likewise with the R2. So we're going to get a no conflict by calling these R1 and R2 as singular values. We just have to know that the fields inside of the structure aren't singular values, but rather they are arrays. And in this case, once again, we're going to leverage our N max, which is probably going to be too large. In other words, the user probably does not want to calculate 100 values, and they may provide us with a value less than 100, in which case we've wasted a little bit of memory, but we'll come back to that as well. Now, if you understand this, then you want to go ahead and proceed to how we are going to collect the information. And this is down here in our /beam /I. Well, none of that really changes. We provide a prompt to the user that asks for the load. We're going to store it in that singular variable W, that singular W, double. We're going to do the same with L, and then we're going to ask the user to provide N, where N is the number of points. At this point, we can go ahead and assign L and N to our beam example structure by using the dot notation. This is different from inside the function because inside the function, we pass the address of the structure. And so as a result, we have to use the dash greater than sign to get access to the value. Outside the structure, we are not dealing with the address of the structure, but rather the structure itself. And so we can simply assign the value directly using the dot notation. Now, once again, don't get hung up on the fact that this variable matches the field name. If anything, that's what we're going to try to highlight here, is that it can, but it doesn't have to. And what we'll do now is we'll calculate our A delta, much like we did in our P5, except we're going to leverage now the beam underscore example dot n. Now you could have done this by using the n alone, the n that was captured from the user by the prompt on line 293. However, though, I want to emphasize the fact that we're using the values that are stored now in the structure. We can do the same thing to monitor or to create our for loop. And now what we're doing is much like in P5, we're assigning the W not to a singular value, but now to each value in the vector to create a distributed load. Now we're going to keep a constant distributed load for this example, but hopefully you can see how that does not necessarily have to be the case. In other words, we can probably combine this with file IO and have some pretty creative calculations. We do the same thing now with the location of the loads by simply multiplying the index times whatever the A delta is. Hopefully by this time you're comfortable with this process. At this point, now that I've sort of set up my structure, I simply pass the address of the structure to my V4 modified. And if the results of that calculation are successful, then we take the first step of calculating the sum of all of the reaction forces. Now you want to keep in mind that this W here is a vector or an array, multiple loads at multiple locations. And so the idea is that each one of them would result in a reaction force at P1 and P2. The corresponding R1 and R2 vectors can then be summed into a single total R1 at P1 and R2 at P2. And that is what we want to ultimately display on the table. We want to show the singular value. And then ultimately what we want to do is we want to display each of those reaction forces, R1 and R2 at a given A, in the CSV file that if you go back now to the instructions, you'll notice is supposed to be n rows and 6 columns, where the 6 columns are the index, the load, the L, the length of the beam, the A, where a given load is applied, the R1 and the R2 for that A. So at this point, let's go ahead and build it. Let's come out to the command line. We'll go ahead and clear this, run our P5 modified /beam/I, enter in the load of 100 pounds, beam length will make 10, and we'll say that we want to apply that load then at 15 points. So n is equal to 15, in addition to this nice little table that we get for the output on the console. We also get a CSV file with the first column being the index of the parallel arrays, the load applied at that index, the length of the beam, which is constant, but now you should see that your A goes from essentially the beginning of the beam to the end of the beam. And these are the reaction forces that are a result of applying a 100-pound load at this location on the beam. And so the second to last column is R1 and the last column is R2, which we have summed now, and you can verify this in Excel, have summed to the values for R1 and R2. Once again, this particular example is not all that interesting because we're keeping a constant loading function across the beam. We could definitely improve on this example by providing then some sort of linear loading or something along those lines, but that's out of scope for this project. Instead, what we want to do is once we're comfortable with the output table as well as the CSV file, we want to very carefully come in here and copy and paste our code into the parametric branch of our triage or switch triage. Go ahead and build it. And then let's go ahead and verify that we have working code. And I believe what I have done here accidentally, let me go ahead and do a Control-Z. I think I might have been careless in my copying and pasting. So let's do this one more time. I want to start here at line 300. And I want to copy down here. And then very carefully here. Yes, I went just a little too far here. There we go. And now if I build this, there are some downsides to copying and pasting. It goes quicker, but you have to be careful. And then you do /beam/p, and we want to provide it with a load. Let's do a different length for the beam, let's say 20, and different value for the number of points, 5. And you'll see now, if we look at our simple supported beam, we have 5 rows with the columns associated with each one of the values. At this point, the only other thing I want to point out is that we are not doing any pre-validation of our values. And specifically, what I want to point out here, and we will cover this in a later video, is that while the W can in fact be negative, and it would make sense, particularly if we have some sort of lifting load due to a wind, but it would not make sense for our L to be negative. And so since we're using both our L and our N to calculate our A array, it would probably not make any sense for us to do this unless they had been validated before we created these arrays. This is a little bit different than our earlier projectile 1D and 2D problems where we didn't actually use the values before calling the function. There's a couple of different ways that we can get around this. For right now, we're going to assume that the user is not putting in invalid data, and we're simply going to build our W and A arrays and pass them to the function. So hopefully you found this video useful. As always, if you have any questions, comments, or concerns, don't hesitate to ask, and thank you for watching.